Hello, let's talk about orbits. First, just a reminder of the force of gravity, which was discussed in the last lecture. And it's this equation, Newton's equation of universal gravitation here, where the gravitational force between two massive objects is equal to this gravitational constant times the mass of each object divided by the distance between them squared. And increasing or decreasing the mass of the objects can change the force, and so can changing the distance between the objects. That can also change the force that's applied. Um, there's also a force vector. Remember, vectors are just showing us how big something is and in what direction it's in. So there's a force vector pointing from each mass toward the other mass. So this is the force that mass one feels from mass two. And then mass two feels a force from mass one that's the same size, but in the opposite direction. And this is an example of action-reaction pairs, or Newton's third law pairs of forces. So the force of gravity acting on two different objects is a third law force, or third law pair. Now we have this example that we're going to do. We are going to rank the force of gravity between these objects from largest to smallest. So 1 second. Okay. So we're ranking the force of gravity, and we just talked about that. The force of gravity is this constant times the mass of each object divided by the distance between them squared. So we'll just do that for each of these. So for A, we have G times the mass of the big object times the mass of the small object divided by the distance between them squared. So that's just nothing special there. That's kind of the standard one. And then we have for B, we have twice the mass of the big object, but then everything else is the same. So that actually just gives us 2 times the force in A, right? It's just that's the only difference is 2, multiplying by 2. And then we have C, which the big mass is the same. The small mass is twice as big, and then the distance is still D. So this one ends up being the same as B, where it's just twice the force in A because we've just increased the mass by 2. Mass of one of them by 2. And then our last example, G, big mass is the same, little mass is times 2, and then our distance is also times 2. So remember, when you're changing the distance by a factor, you're squaring it. So that makes it bigger. So let's see what we get. GMM divided by D squared. I'm just pulling those out. And then we still have this 2 on the top, and then we have a 4 on the bottom because remember it was squared down there. So this is the force in A, and then we have 2 over 4, that's 1/2. So this is half of the force in A. So for the ranking, we say, let's see, B is equal to C is greater than A, which is greater than D. So that's just an example of how we can figure out how forces relate to each other when we change properties of how the force of gravity changes when we change properties between the objects we're looking at. Sorry for the pixelated image, but this is trying to show that if you launch a projectile, which is really just, remember, projectile motion is just when an object is thrown and is experiencing gravitational acceleration. So if you launch a projectile with enough speed, it will travel far enough that by the time it would hit the ground, the Earth has curved away from it because the Earth is round. Surprise to any flat earthers, the earth is round. And that means, and realistically, like a person couldn't actually do this, but the idea still holds. And you could on not the earth, on a small enough planet or something. But the idea is that this lady throws this projectile hard enough that by the time it would hit the ground is gone because it's curved around. And so instead, the ball or the projectile is just falling around the earth. So back in the previous lecture, when I mentioned the space station and I said the astronauts in the station are falling around the Earth, same thing. This is what an orbit is. It's really just falling around a gravitating object. And things that are orbiting experience weightlessness because they're constantly falling, and there's any surfaces around them, like in the space station, any surfaces around them in the space station are also falling. So there's no support force provided that makes them like feel their weight. So tied in with orbits is Kepler's laws of orbits. So the very first one says the path of each planet around the sun is an ellipse with the sun at one focus. So an ellipse, is just like a squished circle, like an extended circle. And the focus of an ellipse, there's two spots in an ellipse, like within the inside of it, that are called the focus. And the sun in our solar system is in one of those spots. And this is one of those examples where circles are also ellipses, but ellipses aren't necessarily circles unless they are the same distance from the middle at every time. So anyway, everything orbiting the sun in our solar system orbits it in an ellipse. Then we have Kepler's second law that says the line from the sun to any planet sweeps out equal areas of space in equal time intervals. And I know that sounds confusing, but really what it means is that the planet moves faster when it's closer to the sun and slower when it's further away. And we can so hold on to that part as the main meaning, but if you want to decipher the actual wording here in the image, what we're seeing here is this is a planet moving, and we have, like it says, a line from connecting the planet to the sun, sweeps out equal area in equal time. So the planet orbits this distance here along the ellipse in the same amount of time as each of these farther away from the sun distances. So it's saying the planet moves really fast when it's close to the sun, but then like really slow when it's far away. And actually, like geometrically speaking, these areas are the same size. Like obviously not the same shape, but the same size. But anyway, the more important thing is just that the planet moves faster when it's closer to the sun and slower when it's further away. And Kepler's third law says the square of the orbital period of a planet is directly proportional to the cube of the average distance of the planet from the sun, which sounds really like a lot and confusing, but it's really just telling us that the larger the orbit, the longer the period. And it's this relationship where it's the period squared, it's proportional. Remember, that's what that wiggle means again, proportional to the radius cubed. So it makes sense, right? That if it's got a bigger radius, it's going to take longer to make the orbit. But there's also like a mathematical relationship between the two. That's the point of Kepler's third law. And like I said, the force of gravity will point from one object to the other. It also depends on the distance, right? Remember, the equation right here, d squared. So when the planet is closest to the star, the gravitational force is largest. And when it's farthest away from the star, it's smallest. So we have our elliptical orbit, we have our star, the sun. This green arrow is our gravitational force. And so at the closest point toward the sun, the force is pointing directly toward the sun and it's the biggest. And then when we're farther away, it still points toward the sun. So like when we're on one of these sides, it's kind of angled. But when we're at the farthest point, it's just like pointing straight to it. And we see that the farther away we are, the smaller our force vector is. And that's just because of the gravitational force relationship, right? Because it depends on the distance, because the masses aren't changing and either is the constant. But the distance does, specifically in elliptical orbits. Speaking of the impact of the distance, we can also look at energy in orbits. So this is obviously a circular orbit. And if we think back to work and energy, if there is no external work done, then the total energy of the system is constant. So as long as nothing is extra is interacting with our planets, stars, etc., then their energy, total energy, is constant throughout the orbit. So we can see a couple of things here with the circular orbit, that unlike the elliptical orbit, the force is the same each time because the distance isn't changing. It's the same distance away. I think this is like a planet and this is like a moon. So the moon is the same distance away from the planet at all times. And that also means that the potential and kinetic energy aren't changing either. Like its velocity or speed is the same the whole time because it doesn't go farther away from the planet. And its potential energy is the same because its distance from the planet doesn't change. But if we're looking at an elliptical orbit, it looks a little different. The distance between the planet and the satellite, or the moon, if you will, or I guess it could just be an actual satellite. Either way, the object orbiting it, that distance changes. At one point, like we saw, it's really close to the planet. So it's moving really fast. And if it's moving fast at that point, then it's got really big kinetic energy. And the gravitational potential energy depends on the relative position of the planet and the satellite, or like how close the satellite is to the planet. That's what it means by relative position, like how far apart they are. So just like gravitational potential energy near the Earth depends on how close an object is to the surface of the Earth, the same thing is happening on a much larger scale. So in order for the total energy of the orbit to remain the same, when the potential energy decreases, the kinetic energy, so the potential energy decreases when it's closer to the planet, and that's when the kinetic energy increases. And then when the kinetic energy decreases, as in when it's slowing down because it's farther away from the planet, then the potential energy is increasing. Yeah, and then I just want you to think about this question. I suppose we can also talk about it, but take a pause and think about this. Where does the satellite have the greatest kinetic energy, the greatest potential energy, and the greatest total energy? So, kinetic energy, that's when it's moving fastest. And when in an orbit is the object moving fastest? When it's closest to whatever it's orbiting. So kinetic energy is biggest at A. And then we want to know about potential energy. And we can think of it in terms of kinetic energy because potential energy is going to be the biggest when kinetic energy is the smallest. And the speed is the smallest, like the satellite travels the slowest when it's farthest away from the planet. So that means that'll be the minimum kinetic energy and therefore the maximum potential energy. So that's going to be at C when it's farthest away. And then it asks about the total energy. But I said if there's no weird uh, external forces acting, then the total energy is constant. So the total energy is the same the whole time. Otherwise, we wouldn't be using conservation of energy. So in the last lecture, we also talked about escape speed, and like connected to when we talked about black holes. And the escape speed is how fast an object needs to move to escape the gravitational pull of a planet or a star or whatever it's orbiting. And I said for a black hole, the escape speed is greater than the speed of light, meaning that something would have to travel faster than the speed of light to escape. But nothing can travel faster than the speed of light. It is the speed limit of the universe, and not in a way where it's like you can go faster than it because if there's no like cops around, you can travel faster than the speed limit. That is not the case in the universe. Nothing can go faster than the speed of light. But every gravitating object has an escape speed. So we can take a look at what those are for our solar system. Oops. So here they are, and let's see. Okay, yeah, so this is the mass of each object in terms of mass of the Earth, the radius in terms of the Earth's radius, but then we have escape speed in kilometers per second. And just for comparison, the escape speed, the escape speed of a black hole or the speed of light is 300,000 kilometers per second. So we can see for our solar system, nothing gets even close to that. The biggest escape speed is for the sun, which makes sense because it has the biggest mass, not math, is only 618 kilometers per second, not 300,000. So plenty of stuff can still escape from the sun's gravitational pull. And then we can just look at, this is kind of listed by mass of the object, right? Because it's going from biggest escape speed to smallest escape speed. So we can see, okay, the sun is over 300,000 times the mass of the Earth, which is huge. Jupiter is over 300 times the mass of the Earth, which is still big, but nothing compared to the sun. Or not nothing, but not very significant. And then Saturn all the way down to the moon, which has a much smaller escape speed. We can look at Earth's escape speed, which is 11.2 kilometers per second, and then look at the moon's of 2.4. That tells you that the force of gravity from the moon is significantly weaker than on the Earth. And then I wanted to show you also, this is the orbits of stars around the black hole at the center of our galaxy, the Milky Way. And you can see Kepler's second law in action here. I mean, you can't see the thing they're orbiting because it's a black hole. But you can tell when, especially this star here in the middle is closest to the black hole because you see it kind of shoot really fast. Okay, ready to watch. There. And we'll do it again. There. It goes really fast. So that is when it's closest to the black hole, the thing it's orbiting. And that shows us something of Kepler's second law. And then this isn't like true time. Like these, they don't orbit this quickly, like as in what we're watching. This is actually images over a 20-year period. So takes a while still. Here's a version of the same data. The hot spots are the stars, and then the dots indicate positions of specific stars at different time points. And then they've traced out the orbits based on the data. So we can see that the red pink dots here, that was that one we were looking at where it would move really quickly. Oh, wait, that's down here. Because it's the same amount of time between each of them. So if they're farther apart, that means they moved faster. Um, so yeah, this is that point where we watched it whip around and then go slower and then whip around. And you can see it with other ones too. This green one, it's gets pretty close and moves fast, but then we don't really have much more data on it. And like this yellow and blue one, the whole time data has been collected, they've been pretty far from the black hole, so we can't see that difference yet. But the same thing will happen for all of them is when they get close, they will move really fast. Here is the image of the black hole, this black hole at the center of our galaxy. It's called Sagittarius A star, and it's Sagittarius because that's the region of the sky it's in. So if you're familiar with the zodiac constellations, you could look in the direction of the center of our galaxy. If you know where, or if you know what the Sagittarius constellation looks like and you can find it, then that is where the direction of the center of our galaxy. So this one, the coloring looks like what we saw in the previous lecture with a different black hole, with a bright disk around a dark center where we can't actually see the center because that is where light can't escape. And then on top of this, there are these lines, and those represent magnetic field lines. So that was just like something they added to the images, I think. I mean, like they could have collected the data in a way that combined magnetic fields and this further information, but honestly, I don't know that much about where the data came from. So, and this black hole was originally discovered by a professor at UW. I don't think he was a professor at the time, but he became a professor at UW. And it's estimated to be 4 million times the mass of the sun. And then I want to show you this graphic compares the two black holes. So the one in M87 that we saw in the previous lecture, and then at the one in our galaxy. So what we're seeing is that this is the M87 black hole, and the black hole at the center of our galaxy is really small and fits within that dark region, way within that dark region of that black hole. And actually, the black hole at the center of our galaxy actually fits within Mercury's orbit. So the black hole in our galaxy fits within Mercury's orbit. That's the planet closest to the sun. And then if we're looking here, here is where Pluto's orbit is, which is kind of like what we might think of as like the edge of our solar system. So our whole solar system would fit within the part you can't get out of the black hole of M87. And then Voyager 1 out here is like the farthest we've sent anything from Earth, like any satellites or things like that. And that would just be outside of that dark region of M87. So just to give you an idea of the gigantic scale of this and of both of these black holes, honestly, but especially M87. Sorry, 1 second. Oh yeah, and Voyager 1 was launched in the 70s. The goal to have it leave our solar system. So it hasn't, I don't think it's quite left our solar system yet, but yeah, that's the farthest we've sent anything. And it would just get out of, I mean, it couldn't actually get out because again, the escape speed. Anyway, going along, but like I said, the black hole at the center of our galaxy, SAG A star, Sagittarius A star, is 4 million times the mass of the sun. And then M87's black hole is 3 to 6 billion times the mass of the sun. So hugely bigger. And we get these numbers in part because obviously we can't weigh either of these things on a scale. We get those values in part from relationships defined in Kepler's laws. And other observations of objects and the things orbiting around them. So anyway, this last bit here was just like kind of a fun for your information. Got a little long because this is my background, astronomy, and I think black holes are cool. So anyway, that's all I have for you. Have a great day.